In this video, I am going to solve GCE Ordinary Level Chemistry, Paper 2, June 2021 session. June 2021 session. Before we continue, please support us by liking this video and subscribe to our channel. Do not forget to hit the notification bell. Thank you for taking your time to subscribe to our channel. Let's start straight away. Question number 1. The following table is a section of the modern periodic table. The letters A to H represent elements in their correct position. A to H are not the usual symbol for the elements. Yeah, that is the periodic table. A, B, C, D, E, F, G, H. Question A. Using the letters from the table, select an element that is 1. Stored in paraffin oil. Element that is stored in paraffin oil. Elements are only stored in paraffin oil because of their high reactivity with air and with water. And an example of an element that is stored in that is stored in paraffin oil and which is highly reactive with air and also with water is sodium. Sodium is an example of an element in the periodic table that is stored in paraffin oil. And looking at the periodic table that we have been given, A represents the element. So the element stored in paraffin oil is A. A is the right answer for that. B part of it. B part of it. A reddish liquid at room temperature and pressure. A reddish liquid at room temperature and pressure. A reddish liquid is a group 7 element. This is a group 7 element. It is not fluorine, but usually is bromine. Usually is bromine. So the element that we can find under group 17 of the periodic table at that position is G. The element is G. So G is a reddish liquid at room temperature and pressure. Let's go to B. Write the electronic configuration of B. Capital letter B is placed in group 2 of the periodic table. This is placed in group 2 of the periodic table. And the electronic configuration is we have 2, 8, that is 10, and the 2 is 12. So obviously B could be a letter, it could be magnesium. B could be magnesium, but it belongs to group 2 of the periodic table. So we have 2, 8, 2. Sub 2 of it. Why is B classified in group 2 of the periodic table? Why is B classified in group 2 of the periodic table? We can classify B based on the electronic configuration. Based on the electronic configuration, we can classify B in group 2 of the periodic table because it has 2 valence electrons. It has 2 valence electrons. I mean 2 electrons in its outermost shell. 2 electrons in its outermost shell. So it has 2 valence electrons. That is 2 electrons in its outermost shell. You know, elements are classified into groups and periods. And elements are as I said, elements are classified into groups and periods. And the elements placed in group 1, elements in group 1 have 1 electron and have only 1 valence electron. Elements in group 2 have 2 valence electrons. Elements in group 3 have 3 valence electrons. Elements in group 4 have 4 valence electrons, right to group 17. Elements in group 17 have group 17, or what is usually called group 7, have 7 electrons in their valence shell. And obviously the inert gases or the noble gases, they have 8 electrons in their outermost shell, or they have 8 valence electrons. So we are saying that elements that are we are saying that B is classified in group 2 of the periodic table because it has 2 valence electrons. That is, it has 2 electrons in its outermost shell. C. The element E has a relative atomic mass of 27. Give the composition of an element E. Or you see from groups, it has atomic mass of 27. From 27, we have, it has the proton number is 13. The number of electron is 13, and the number of neutron is 14. So because the number of neutron plus the number of proton will give us the mass number. So if we have the electron number to be 13 or the proton number to be 13, 27 minus 13 will give us 14, which is the number of neutron. D. 2 elements X and Y have atomic. 2 elements X and Y have atomic numbers of 6 and 17 respectively. Write the formula of the compound formed between X and Y. It should be noted that the electronic configuration of the element with atomic number 4 will be 2. Element with atomic number 6 will be 2, 4. Then the electronic configuration of the element with the atomic number 17 will be 2, 8, 7. Is 287. We are saying that 27. We are saying that X has 4 electrons in the outermost shell. X has 4 valence electrons. X has 4 valence electrons. X has 4 valence electrons, and Y has 7 valence electrons. So now the charge of this will need 4 electrons, and this will only undergo a covalent bonding. So covalent bonding. So X will represent, let me say X is representing chlorine, and Y is representing chlorine, and X is representing carbon. And we have a compound we have a compound like carbon tetrachloromethane, like this. We will have a carbon sharing electrons with this. So in that case, so we will have a compound of this nature. So the formula of this will be XY4, because it will undergo what we call a covalent bonding. So it would undergo something like this. This is X, and this is it will undergo covalent bonding. This is Y. Y has 7 valence electron. X has 4 valence electron. So it cannot undergo ionic bonding. It can only undergo covalent bonding, sharing of electrons. So it will be XY4. So that can only be the formula for it. For this, that can only be the formula for a possible formula for X and Y, based on this covalency here. Identify the bond type in the compound in D1. The bond type is a covalent bond. Sodium chloride has the formula NaCl. Identify the charge of the metallic ion. In the metallic ion here, the charge on the sodium will be a positive charge. It will be a positive charge. Question number 2. This question concerns the following: sodium, silver, calcium, iron, and aluminum. Select from the element a transition metal used as a catalyst. Of course, sodium, iron, finely divided iron is used as a catalyst in the industrial production of is used as a catalyst. A finely divided ion is often used as a catalyst. So iron is a transition metal, and finely divided ion is often used as a catalyst. So that's why iron is used as a catalyst. An element that forms an amphoteric oxide. A group 13 element usually forms an amphoteric oxide. For instance, aluminum. Aluminum will form amphoteric oxide. Aluminum oxide is amphoteric oxide. It can react both with an acid and with a base. So for that reason, aluminum is the element that forms amphoteric oxide. That is aluminum. Number 3, an element that is a basic constituent of bones. An element that is a basic constituent of bones. You know that the bones, the normal human bones, there is an element there that can give strength to the bone, and the element is a group 2 element, and that group 2 element is calcium. That group 2 element is calcium. So it is calcium here that is there. Arrange the elements in order of decreasing reactivity. starting from the most reactive. If you look at the elements up here, arrange the elements. Arrange the elements in order of decreasing reactivity, starting from the most reactive. If you look at the elements here, from sodium, silver, calcium, iron, and aluminum, you will see that the most reactive is sodium. This is followed by calcium, and this is also followed by aluminum, and it's also followed by after aluminum is followed by after aluminum we have sodium, we have calcium, we have aluminum, we have iron, we will have the last one should be silver. Silver should be the last one. The last one should be silver. Silver should be the least reactive one. Silver should be the least reactive. Sodium, calcium, aluminum. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So we have sodium, calcium, aluminum, iron, and silver. Okay, the element calcium reacts with dilute hydrochloric acid. State one common observation. Remember that when a metal, when you put a metal in a dilute acid, for example, the hydrochloric acid, there is effervescence. Effervescence is observed. There is effervescence. A gas is being released, and that gas that is being released is a hydrogen gas. When a metal reacts with hydrochloric acid, a hydrogen gas is being released. The hydrogen gas is always released. So, one common observation is effervescence. You can say effervescence, you can say bubbles of gas produced, you can say fizzing, you can say fizzing. These are common words you can use. You can say effervescence, you can say fizzing, you can say bubbles of gas, and you can also say a gas is released. All these are acceptable by examiners. I said you can say fizzing, fizzing, you can say fizzing, bubbles of gas, bubbles of gas, so fizzing, bubbles of gas, anything you write fizzing, it is acceptable. Bubbles of gas is acceptable. Effervescence is acceptable. Now, write a balanced equation. Write a balanced equation for the reaction taking place. You know, there is calcium is more reactive, so calcium will displace hydrogen. Calcium will displace hydrogen. Calcium will displace hydrogen. So in that case, there is calcium plus hydrochloric acid. Dilute hydrochloric acid is aqueous, so it will displace the hydrogen, and it will form calcium chloride with a hydrogen gas that is being released. Make sure you balance the hydrogen gas with the two, you put two to balance the hydrochloric acid with the two of the hydrogen gas. Okay, that is okay. Now state the product formed when a piece of sodium reacts with water. When a piece state, we are just to state when sodium reacts. Remember that when sodium is put in water, even though the reaction is very vigorous, even though the reaction is very vigorous, but at the end of the day, sodium belongs to group 1 of the periodic, is a group 1 metal, and what will be formed there will be sodium hydroxide. It is a sodium hydroxide that will be formed. It's a strong alkali that will be formed. So when a piece of sodium reacts with water, the product form will be a sodium hydroxide and a hydrogen gas. Remember, I said a hydrogen gas is also released. A hydrogen gas is also released in the course of the reaction. So there are two products, sodium hydroxide and hydrogen gas are produced. E. Identify the element that is used for making coins and cups. Of course, coins, you look at the nature of the coins, the shining nature of the coins, you will see that it is not a pure element. They are all alloys. They are all alloys they are all alloys, because the alloys themselves will give strength to the coin. It will give strength to the cups. So now we have three elements. We have three elements that are used for the making of coins and the cups. We have alloys from copper, alloys from silver, and alloys from gold. There are golden cups made of the alloys, not only gold, alloys. Alloys from gold, alloys from silver, alloys from copper. They are all used for the making of coins and cups. Select an element that gives a characteristic intense yellow flame color. If you burnt element as there are some characteristic elements here which I need to show you. Okay, look, identification of metals in compounds when burnt in oxygen. Identification of compounds when burnt in oxygen. You see, when there is a all these are salts of chloride, when burned in oxygen. This lithium chloride, you see the flame of lithium chloride. That is the flame of lithium chloride. That is the flame of sodium chloride, golden yellow. That is the flame of potassium chloride, lilac. That is the flame of rubidium chloride, cesium chloride, calcium chloride. That is the flame of strontium chloride. That is the flame. The flame color for barium chloride. The flame color for copper 2 chloride. That is for titanium chloride, and these are different. So to cut everything short, this is just a flame. These are the different. These are the identification of metals in compounds burned in oxygen, and all of them are all salts, chloride salts. So now sodium is golden yellow. So if we go back to our question, we're asking about what color will sodium give? what color will sodium give? You should be able to know that sodium will give a golden color. Sodium will be able to give a golden color. So now, F. Select an element that gives a characteristic intense yellow flame color. The element here is sodium. It is sodium. From all the elements here, it is sodium that can give. Only sodium can give an intense yellow color. Only sodium. Only sodium can do that. Only sodium can do that. So now our answer is sodium. Our answer is sodium. So altogether you have a total of 10 marks here. Question number 3, it has to do with equilibrium. Equilibrium and reversible reaction. So now we are starting with nitrogen 3A. Nitrogen and hydrogen react reversibly as shown by the following reaction. This is nitrogen here, and this is nitrogen with the forward reaction gives 2 moles of ammonia. The backward reaction will give 1 mole of nitrogen plus 3 moles of hydrogen. And the enthalpy change, the energy change for this reaction is negative 94 kilojoule per mole. The question now states, state one source of hydrogen. State one source of hydrogen. State one source of hydrogen. That one source of hydrogen. You know, we have been dealing with hydrogen, the composition of hydrogen in the air, and even when we were doing hydrocarbon, how we can get hydrogen from cracking of large hydrocarbons. So now, one source of hydrogen in this reaction here is cracking of hydrocarbons, or from steam. Cracking of hydrocarbons or from steam. You can crack large hydrocarbons into smaller ones. Large hydrocarbon alkanes, larger alkanes can be cracked into alkenes and hydrogen. So now cracking of hydrocarbons or from steam. Then state one source of nitrogen. Nitrogen is found in the air. Nitrogen is found in the air. And you know it very well. Nitrogen is found in the air. You know it very well. So nitrogen in the air, we can only get it from fractional distillation of liquefied air. Fractional distillation of liquefied air. Nitrogen from fractional distillation of liquefied air. That's where you can get nitrogen. 3A2. State what would happen to the equilibrium position when pressure is increased. Excellent. You know that in an equilibrium like this, this is a gaseous reaction. We have 2 moles on the right and 2 moles of gases on the right, and we have altogether 3 plus 1, we have 4 moles on the left. So now when the pressure is increased, what happens? Because they have said state what will happen to the position of the equilibrium. Know that we have to apply Le Chatelier's principle. Le Chatelier's principle is very, very important. So in this situation, Le Chatelier's principle only comes in to do the opposite. It only comes in to do the opposite. When you increase the pressure, it comes in to decrease the pressure. So it comes in to do the opposite. It comes in to oppose. So what is actually happening here is when we increase the pressure, according to Le Chatelier's principle, the system must react in such a way to oppose the equilibrium position, and a new equilibrium is established. And by doing that, the equilibrium will do what? The equilibrium will shift to the region of low number of moles. Now, on the right, we have 2 moles. On the left, we have 4. So increasing the pressure does what? Increasing the pressure will shift the equilibrium to the area or to the direction where there are few number of gaseous moles. So the equilibrium will shift to the right. And when the equilibrium is shift to the right, it helps to do what? It helps to decrease. It helps to decrease the pressure. It helps to decrease the pressure. Like I earlier said, Le Chatelier principle only comes in to oppose the equilibrium position. When the equilibrium is high, it comes in to decrease it. When the equilibrium is decreases, it comes in to increase it. So in this case, there is high pressure. There's high pressure. So Le Chatelier's principle comes in to decrease it by doing what? By shifting the equilibrium position to the right. Okay, temperature. State what would happen to the equilibrium position when the temperature is increased. Now, when the temperature is increased, according to Le Chatelier's principle, now this is an exothermic reaction. It is -9.4, meaning that it is an exothermic reaction. So now, if we are increasing the temperature, we are now favoring what? The endothermic direction. And endothermic direction, it means what? Decomposition of the ammonia into nitrogen and the hydrogen. So we are indirectly saying that increasing the temperature will shift the equilibrium to the left. It will shift the equilibrium to the left. It will favor the endothermic direction. So it will shift increasing the temperature will shift the equilibrium to the left. Now, 3. The yield of ammonia can be increased by withdrawing some ammonia from the equilibrium mixture. Of course, ammonia is usually withdrawn. If ammonia is not withdrawn as time goes on, what happens? It is decomposed back into nitrogen and decomposed back into nitrogen and what? And hydrogen. So the yield can only be increased by withdrawing some ammonia from the equilibrium mixture. Identify and state the principle that account for this. The principle is Le Chatelier's principle. Le Chatelier's principle. Okay, state Le Chatelier's principle. Okay, Le Chatelier's principle states that if a system in equilibrium is subjected to a change. Once more, if a system in equilibrium is subjected to a change, the system must react in such a way to oppose the change, thereby establishing a new equilibrium. Once more, let me state Le Chatelier's principle. If a system in equilibrium is subjected to a change, the system must react in such a way to oppose the change, thereby establishing a new equilibrium. B. You are given the following reaction: marble chips, that is calcium carbonate plus dilute hydrochloric acid, and you will have both calcium chloride, carbon dioxide, and water. State 2 factors that will affect the rate of this reaction. Of course, the rate of this reaction, calcium carbonate is solid. So the rate of the rate of this reaction can only be increased by doing what? By increasing the surface area of calcium carbonate. Increasing the surface area of calcium carbonate. If you increase the surface area by grinding it to what? To powder, you increase the surface area. If you grind the solid to the to the powdered form, you are increasing the surface area. That's one thing, increasing the surface area of the calcium carbonate. Two, increasing the concentration of the hydrochloric acid. By increasing the concentration of the hydrochloric acid and increasing the surface area of calcium carbonate, what happened? The rate of reaction is going to increase. Okay. Two, the volume of carbon dioxide can be produced, the volume of carbon dioxide gas produced is recorded from a graduated syringe. State and explain what could be done to the concentration of hydrochloric acid in order to obtain more carbon dioxide within a shorter period. The statement is increase the concentration of hydrochloric acid. Increase the concentration of hydrochloric acid. Increase the concentration of hydrochloric acid. If you increase the concentration, my arrows that are going up are showing increase. If you increase the concentration of hydrochloric acid, there is going to be more collision of particles. There's going to be more collision of particles. And subsequently, there's going to be an increase in the rate of reaction. Subsequently, there is going to be increased production of carbon dioxide. Once more, increasing the concentration of hydrochloric acid will increase the collision of particles, thereby increasing the rate of reaction and finally resulting in an increase in carbon dioxide production. Okay, it takes us to question number 4. Question number 4. This question concerns some organic compounds belonging to the following homologous series. We have propanol. There's propanol there. There is propanol. There is ethanoic acid. There is ethene, and there is ethane. What is a homologous series? It has to do with homologous series because here A, we have alcohols. B, we have carboxylic acids. C, we have alkanes. And D, we have alkanes. All of them are different homologous series. What is a homologous series? What is a homologous series? A homologous series, excuse me, homologous series, once more. These are compounds. These are compounds. Homologous series are compounds. These are compounds. I said these are compounds having the same general formula and chemical properties, but physical properties that show a constant gradation. Compounds having the same general formula and chemical properties, but physical properties that show a constant gradation. When I say constant gradation, I mean a melting point and a boiling point constantly decreasing, or increasing. B. Select from A to D an unsaturated compound. An unsaturated compound here is an alkene, is C. It's an alkene, which is ethene, is C. 2. A compound that readily undergoes substitution reaction with halogen at room temperature and pressure. At room temperature and pressure, only alkanes will do that. Only alkanes will do that. At room temperature and pressure, only alkanes will do that. They will do substitution under UV light. The UV light will be used as a catalyst. Only alkanes will undergo substitution reaction with halogen at room temperature and pressure, and UV light is used as a catalyst. So we have D. D is an alkane. C. Compound A and B. Compound A and B, I'm talking of alcohol and acids. Compound A and B react in the presence of react in the presence of concentrated sulfuric acid. They react in the presence of concentrated sulfuric acid. Write an equation for the reaction. Compound A and B. Compound A and B. Compound A and compound B react in the presence of concentrated sulfuric acid, and they will do this. So in this case, there is going to be what we call esterification. There's going to be esterification. When compound A and B react, there's going to be esterification. A and B will react to form we have compound A, that is ethanol with this. Okay, we will have this compound A. Write an equation. For compound A, we will have CH3, 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 yes, I am. It will react with the acid. The acid will be, yes, it will be that will be esterification. Sulfuric acid will do that. It will be write an equation for the reaction. We will have a CH3 yeah, plus water. A molecule of water is being released. So we will call this, the product form is 1, 2, 3 propyl ethanoate. 1, 2, 3 propyl is propyl ethanoate. Will be propyl ethanoate. Our product form will be propyl ethanoate. Okay. When an alcohol reacts with an acid, when an alcohol reacts with an acid, when an alcohol reacts with an acid, an ester is formed. And the ester here is the propyl ethanoate that is formed. Identify the family of the organic compound to which the main product belongs. The family to which the main product belongs. Identify the family of organic compound to which the main product belongs. An ester. It belongs to an ester. It belongs to an ester. It belongs to an ester. Give the different structural forms of compound A. Give the different structural forms of compound A. Compound A is it has 3 carbons. Compound A has 3 carbons, 8 hydrogens, 1, 2, 3, 4, 5, 6, 7, 8. Yeah, it has 3 carbons, 8 hydrogens, and 1 oxygen. So now the different forms of compound A, we have ether. Give the different structural form of compound A. We have ether, we have alcohol, that is secondary alcohol, and we have a primary alcohol. So we have ether. Give the different structural forms, only the forms, not the names. Okay, yeah, can name them later on. Okay, how are these structural forms called? We call them isomers because they have the same molecular formula. They have the same molecular formula. but different structural arrangement. They have different structural, they have different structures, but the same molecular formula. Okay, identify the reagent that is used to distinguish between compound C from compound D. Compound C from compound D. C is unsaturated, that is an alkene, that is ethene, and D is ethane, alkene and alkane. D. Okay, reagent, we can use bromine water, Observation, only compound C, that is the alkene or the ethene, only the compound C or the alkene, or you can still call it the ethene, only compound C will decolorize bromine water. That is enough. Define a mole. I can define a mole as this is the amount of substance. This is the amount of substance which contains 6.02 times 10 to the 23rd specified particles. The specified particles I'm talking of atoms, molecules, ions, or electrons. So you can now say the mole of a substance is the amount of substance which contains 6.02 times 10 to the 23rd ions. 6.02 times 10 to the 23rd molecules or electrons. So that's why I say specified particles. I put in bracket atoms, molecules, ions, or electrons. Okay, the B part of it. 5.4 grams of magnesium react with excess dilute hydrochloric acid. How many moles of magnesium are present in 2.4 grams? In this type of thing, you have to write the equation. What the equation, this is stoichiometry. We need to know what quantity is reacting with what. Okay, after writing the equation, even though the equation is not needed on Roman 1 here to calculate the number of moles of this. So, write the equation because we'll use the equation later on. We'll write the equation as magnesium plus hydrochloric acid to give magnesium chloride and hydrogen gas that is being produced. Yeah, no problem, hydrogen gas that is being produced. No problem. Okay, now remember there is a formula, we call it the moles. Moles equals to mass divided by relative atomic mass. So the given mass divided by the relative atomic mass will give you the number of moles. So the given mass was 2.4. 2.4 divided by the relative atomic mass of magnesium. The relative atomic mass of magnesium is 24. And if it is 24, if the relative atomic mass of magnesium is 24, let me see. If the relative atomic mass of magnesium is 24, then we have it as magnesium yeah, 24.3. It is 24.3. 24. Okay. If it has been given as 24, no problem. It's okay. Magnesium has been given as 24. No problem. For easy calculation, 2.4 divided by 24 gram per mole. So we will have, what we are going to have here will be 0.1 mole. 0.1 mole. We are going to have 0.1 mole. 24. If magnesium is given as 24. So now that is it. Okay, to calculate the number of moles of hydrogen, remember that let me put it here. If one mole if one mole of magnesium can give, from the equation, can give 1 mole of hydrogen, then 0.1 mole of magnesium will give 0.1, it will just cross multiply, and it will be 0.1 mole of hydrogen. So the number of moles of hydrogen equals to the number of moles of magnesium. The number of moles of hydrogen equals to the number of moles of magnesium. But molar gas volume, the molar gas volume is equals to what? 1 mole of a gas is equals to 24 cm cube. 1 mole of a gas occupies a volume of 24,000 cm cube, or 24 dm cube. You have been asked to calculate the volume at room temperature. So now, calculate the volume of a hydrogen gas evolved at room temperature and pressure. When they are talking at room temperature and pressure, please, you have to involve the molar gas volume. The molar gas volume, you have to involve it when it has to do with room temperature and pressure. And remember that 1 mole of a gas occupies a volume of 24,000 cm cube, or 24 dm cube. 24,000 cm cube, or 24 dm cube. So now, if 1 mole of a gas is equal to 24 cm cube, then 0.1 mole of hydrogen will occupy what? You cross multiply. 0.1 times 24 is equal to 2,400 cm cube, or in other words, 2.4 dm cube. That will be the volume. That will be the volume. If 1 mole of a gas is 24,000, then 0.1 is equal to what? You multiply 0.1 times 24,000, and you have it. You can either put it in dm cube, or you put it in cm cube. Everything is acceptable. Now, in the extraction of iron, carbon monoxide is used to reduce hematite. Hematite is iron 3 oxide. That's hematite. Okay, now write an equation to show how the carbon monoxide is formed in the blast furnace. Okay, carbon monoxide. Okay, this is a reducing agent. Carbon dioxide plus carbon, which is solid, it will give carbon monoxide. That is the equation. It has, from 0, it has reduced carbon from 0 to what? Here is -2. It has oxygen is -2 +2. It has oxidized, sorry, it has oxidized carbon from 0 to +2. Now write an equation for the reduction of hematite to iron. Okay, now to iron, reduction of hematite to iron, we wouldn't have to use the carbon monoxide that was formed here. The carbon monoxide that was formed in the blast furnace will be used in the reduction process. So the hematite, which is the iron 3 oxide, plus the carbon monoxide will give us the iron, plus the carbon dioxide. This is the reduction process. Now identify the substance that is used to remove sandy impurities. The substance that is always used to remove sandy impurities. The substance that is always used to remove these sandy impurities here is limestone. Limestone will remove all the impurities. Limestone also remove impurities like silicon dioxide. It also remove impurities like silicon dioxide. Okay, give one use of iron in our homes. In our homes, iron is widely used at home. For instance, it is used in construction. It is used as iron rods for the construction of our homes. It is used as iron rods for the construction of our homes. It is also used for household utensils such as cutlasses. It is used as iron rods for the construction of our homes. It is also used as household utensil. For instance, cutlasses. Go to 6. Question number 6. The B part of it. Excuse me. Sketch and name the laboratory apparatus used during acid-base titration. Excuse me. Sketch and name the laboratory apparatus used during acid-base titration to transfer 25 cm cube of a base into a conical flask. Once more, learners, if you have watched our previous video on basic laboratory equipment, their uses and how their uses, you will know you should be versed with all this. I will refer you back to watch our previous video on basic laboratory equipment. You will see all this. You will see the different laboratory equipment. You will see how the purposes they are used for. You will see the purposes they are used for in the laboratory. If you have done this, this will be an ABC for you. However, before you are going there, this is an example of, this is a pipette. This is a pipette. A pipette is used to pipette the base into the conical flask. So if you were to sketch, this is what you are going to sketch. The pipette, this is what you are going to sketch. This one is better than this one. This is what you are going to sketch. If you were to sketch, this is the diagram that is expected of you. You sketch it, you label it, the pipette. Okay, let me go back again. Now, that is left for you. This is the pictures here. Then, sketch and name the laboratory apparatus used during acid-base titration to prepare a standard solution. To prepare a standard solution, you will use a volumetric flask. On your right here, this is a volumetric flask. A volumetric flask is there. It is labeled 100 ml. I mean 1,000 ml. It is also labeled 1,000 cm cube or 1,000 cubic centimeters. You will either see 1,000 ml or you will see 1,000 cubic centimeters. This is what is used to prepare a standard solution. We label it volumetric flask. You label it a volumetric flask. Okay. B. The B part of it. In a titration experiment, a student transferred 25 cm cube. A student transferred 25 cm cube of sodium carbonate solution into a conical flask and titrated the solution and titrated with dilute hydrochloric acid from an equipment P. Draw and name the equipment P. Again, this is the equipment P. This is the equipment P. This is the equipment P where you are titrating into the conical flask. Either this, we call it the burette. Equipment P is called the burette. This, you can sketch this diagram here. This is where this the acid. The acid is put into this. This is graduated from 50 to 0. The last point here is 0. You start reading from here. So it is graduated from 50 to 0. This is the burette rate. So this is the diagram here. You can sketch this one or you sketch this one. So that is P, the burette rate, where the acid is placed. Okay, the following table shows results of accurate titration. Accurate titration. We have second titration. We have second titration, a second reading. We have first reading. We have the titra. They say complete the table and determine the volume of the dilute hydrochloric acid. Of course, this is a titration. They have just carried out two accurate titration. They have just carried out two accurate titration. They want us to complete it. I told you that the first reading is the first burette reading. The first reading is the initial burette reading. Then the second reading is the final burette reading when you have arrived at your endpoint of your titration. So now everything has been done here. You have been asked now. The only thing to do now is to have your titra here. To have your titra here, you will subtract based on the result here. You will subtract the first reading from the second reading. This is your final reading, which is 24.8. So to have your titra here, it is 24.8 minus 2.5. That was where you started. And your titra is the volume you have used. The titra is volume you have used for titration. The volume that has reacted with the sodium carbonate. So here too, you will subtract this one, 22 from 44, and it's 44.6 minus 22.4. You will have 22.2. This is the volume that has reacted. Then, okay, complete this. Okay, calculate the concentration. Okay, complete the table and determine the volume of dilute hydrochloric acid. The volume of the dilute hydrochloric acid. You cannot take the volume of this titration. You cannot take the volume of this second titration. What you will do is you will look for an average. We call it the mean tetra. The mean tetra, an average titration. So the average or the mean tetra of this will be what? Will be this value and this other value divided by 2. You have it. Mostly, if there are more than 4 titration that you carried out, the mean tetra will be, you will take it, but from the results, concordant result that are just about 0.1 difference, a difference of 0.1. So this one too is just a difference of 0.1. So in that case, we have taken these two. So 22.3 plus 22.2 divided by 2. This is our average titra, or what we call the mean titra of hydrochloric acid that has been used for the titration. And this is what we are going to use in our calculation. So now calculate the concentration of the sodium carbonate. If 0.1 molar hydrochloric acid was used. Okay. Remember that this is when you write this equation. When you write this equation like this, you will use this equation for your calculation. Okay. For instance, here we will use a formula: molarity of acid, volume of acid, molarity of base, volume of base equals to the mole ratio. That is mole ratio. The number of acid that have reacted all over the number of base, the number of moles of acid that have reacted all over the number of base of the number of moles of base that have reacted. Now that we are looking but for the concentration of the base, we are looking for the concentration of the base from the question. The question says calculate the concentration of sodium carbonate. We are looking for the concentration of the base. So now what we will do is we will look but for MB. That is method 1. We'll look for MB. MB will be what? We will do this, and all the volume, once more, all the volume must be in dm cube. the volume must be in dm cube. You must convert the volume of the base and the volume of the acid in dm cube. So now we have converted Ma 0.1 times this everything, the volume in dm cube, and this is our molarity of the base. Now we can still use another method. Method number 2. Method number 2, the number of moles of acid. We can calculate the number of moles of acid by doing what? By multiplying the concentration of the acid, by multiplying the concentration of the acid by the volume. And the volume will be what? The volume will be in, by the concentration, by multiplying the concentration and the volume, we'll have the number of moles. And the volume will be in dm cube. We have to convert it in dm cube. So when we divide that volume that we had for hydrogen, when we divide that volume that we had for hydrochloric acid, then we'll multiply it by the molarity, and we'll have the number of moles for hydrochloric acid. Then again, the moles of the sodium carbonate. Remember that there are 2 moles of hydrochloric acid that have reacted with 1 mole of sodium carbonate. In that case, we have to divide the volume, we have to divide the number of moles by 2 to have the number of moles of this one, and that will be 0.011 moles. Now we have got the number of moles of sodium carbonate. We can use the number of moles of sodium carbonate now to calculate our concentration. And what is the concentration? Concentration is a what? Is moles divided by the volume in dm cube. So we now know the volume of sodium carbonate was the one that was pipetted into the conical flask, that is 25. We will divide it by 1000, we will have 0.025. Then we divide the number of moles, so it will be 0.0011 divided by 0.025. When we divide that, we will have what? We will have 0.044 mole per dm cube, or 0.044 molar. That is what we will have, and that will be the concentration of sodium carbonate. And that is how you can get it. Okay, we move ahead. 3. Methyl orange is used for this titration. Methyl orange. What color change is observed at the end? Initial color and the final color. Okay, imagine this methyl orange. I just brought you something here for your revision purpose. This methyl orange. A methyl orange is between 3 and 3 to 4.4 pH. Is between 3 to 3.4. It's still within acidity. So the final this thing, methyl orange, after putting it in an acid, the color change will be red. It is red here because we don't want the pH of 1, 2, 3 in acidity. The pH is red. It is still red. So the color change will be red. The color change for methyl orange will be red. Initially it was orange. Now it is red. It is methyl orange. Initially it was orange, but now the final color will be red. During an acid-base titration, how many times do we usually carry out the titration process? Fellow learners, remember that there must be a first titration. We call it a rough titration. A rough titration is to enable the person working, the investigator, to know the range of the volume that is reacting, the range of the titrant. So when you carry it, and it is usually carried out very fast, you carry out the rough titration very fast to know the range, so that when you are carrying out accurate titrations, you should stick towards that range. So we have a rough titration and 3 other titrations, making a total of 4 titrations. Now, in an experiment to determine the formula of an oxide of copper, the following results were obtained. I have the mass of both alone, which is 8.320. The mass of both and oxide, which is this, mass of both and copper, we have this. Determine the formula of oxide. Well, after the deduction, I have the mass of copper to be 2.048 and the mass of oxygen to be 2.55. Then the relative atomic mass of copper is 63.5. And the relative atomic mass of oxygen atom is 16. So now the relative atomic mass of oxygen atom is 16. But if we are dividing it by oxygen atom, it is 16. So now when we divide it, we will have 0.032 and 0.159. Then we have to divide it by the smallest, the smaller one. So we'll divide everything by 0.032, 0.033. We will have 1 and 5. And if I were to determine the formula of the oxide, this will be the formula of the oxide. But unfortunately, copper does not exist as copper 2, copper 5. Copper does not exist as copper 5, but this is the formula I have determined from here. Okay. For further, we have some laboratory work here. Some laboratory work carried out here. In this laboratory work, we have, in the laboratory work here, a student was provided with three salts, A, B, C, and D, A, B, and C, alongside some laboratory equipment and the following reagents. Some of the information is missing, but I will only answer questions on the information that is available. Some of the information is missing. Okay. Aqueous sodium hydroxide, aqueous barium chloride, acidified silver nitrate, and dilute hydrochloric acid. A series of tests were carried out as shown on the following table. Okay. What we will do is, the first test is a flame test is carried out on the solid sample of salt A, and the presence of calcium. The presence of calcium will indicate orange red, because if you look at the identification of metals here, calcium here is showing calcium here. The ions, they are the ions of the metal that are giving out this color. They are the ions of the metal that are giving out this color, not the halogens. They are the ions. So here it is calcium chloride salt, but it is calcium ion that is giving this, and it is orange red. So it is orange red there. B, a solid sample of A is heated in a test tube. A brown gas is evolved. That one I can't get it. I can't get it. A brown gas is, I don't know. I'm still suspecting of nitrous gas, NO2 or NO. A brown gas, NO2. This gas, gas. Okay. B, salt B is dissolved in water to give a solution. A reddish brown precipitate is formed. The presence of a reddish brown indicates the presence of ion 3 ions. Then to 2 cm cube solution of B is added 2 drops of aqueous sodium hydroxide. A reddish brown precipitate is also formed. This one, the conclusion. 3 to 2 cm cube of solution B. Time is cutting me short. To 2 cm cube of B is added 2 drops of acidified silver nitrate. Silver nitrate, the presence of bromide ion indicates a cream precipitate, a halide. Then C, a bluish green flame color is seen. Bluish green color is seen. We are talking of the presence of a titanium ion. Carry out a flame test on salt C. C, carry a flame test on salt C. On 2, sorry. To 2 cm cube of aqueous solution of salt C is added 2 drops of aqueous barium chloride, followed by 2 cm cube of dilute hydrochloric acid. On first addition, there is effervescence. First addition, there is effervescence, followed by white precipitate of barium sulfate. 2 drops of barium chloride followed by 2. 2 drops of white precipitate barium. I can do it as barium. Okay. White precipitate of barium chloride. Okay. White precipitate of barium chloride. Okay, barium chloride followed by 2. Presence of sulfide ion. Now to a solid sample of C. 5 drops of dilute hydrochloric acid, effervescence with a small smell of burnt match. Okay, the presence of sulfur. Sulfur. Okay. Okay, we can now identify. This one that I was saying. Okay, B, we can identify B to be. We can identify B to be iron bromide. B, we can identify B to be iron bromide, iron 3 bromide. We can identify B to be iron 3 bromide and C to be barium chloride. This is all the information I have. Barium, calcium metal, barium, B for that. Okay, thank you for watching. Thank you for watching. Thank you for watching. Thank you for watching. Thank you. We'll have more for O levels, for O level, GCE O levels. We will be following with more MCQ questions and answers. Thank you. just before you go, I just want to remind you that if you haven't subscribed to our channel, please support us by subscribing to our channel, and do not forget to hit the notification bell. Thank you for your support once more. Bye bye. Wishing you best of luck.